Okay, hello everyone. Thanks for being here. Today I want to talk about doing logics in some algebraic code. So by algebraic codes, I mean that the code words of the code can be expressed in terms of some polynomials. The precise definition for each algebraic code is a bit different, but usually I mean that the code words can be written as an evaluation of certain polynomial at different places. So I will show explicit examples of this later. But for now, on a high level, I want to say a few things. So first of all, if you consider the logical CNOT gates, they usually come from the automorphism permutation of the code. And by considering the intersections of code words, we can also derive certain diagonal gates of the code. Diagonal means it's a phase gate, for example, S gate, CZ gate, or even CCZ or T gates. Okay, so let's get started. So I've been working on algebraic code for the past years. And so in this first paper, in this 2024 paper, I worked on two families of code. One is k=1 punctured quantum Reed-Muller codes. So here we got a pair of codes where this d=15 code can do transversal Clifford group. And this d=7 code is a bit special. It can do transversal T. And I also proposed a way to transversally code switch between them. And there I also consider a high-rate family of quantum Reed-Muller codes. And I show that by using transversal and full transversal gates, the full Clifford group can be achieved. So the problem here with this family is that the rate is too high, so that the depth of doing the logical gate is actually not controlled. It's very bad. That leads to this follow-up work, which was put on arXiv last week, where we consider something called phantom code. So the definition of this is that we can do arbitrary logical CNOT circuit, no matter what's the depth, from automorphism permutation only. And this family, this phantom QRM family, is actually derived from this high-rate family here by gauging out some of the logical qubits. By that, I mean like freeze them either into all plus or all zero. This is promoting them into X stabilizer or Z stabilizer. So you will see later that by doing this, we actually get very good control on the depth of the logical circuit. So there I also consider another family of code, which is related to another project I'm doing. Today I don't have the time to go into detail of those, so I will only focus on these two quantum Reed-Muller code-based constructions. Okay, so here's the schedule. I want to start with the k=1 code, and especially tell you why this d=7 code admits transversal T gate. And then I will go to the phantom codes, encoding more qubits, and then I will talk about like implementation here. So the idea of this talk is like more like a tutorial instead of like showing you the results. So if you have any questions, just feel free to ask at any point. So an important convention I will be using throughout the talk is that I will write down a CSS code in this way. So I will only specify the X logical generators and the X stabilizer generators of the code, but not Z stabilizer. This is because a Z stabilizer commute with some X logical generator and X stabilizers. So Z stabilizers will be the kernel of this matrix. So this is effectively enough to specify a CSS code. So this will be a binary matrix, and here you have k rows for the generators, logical generators. And if I write down a 0, 1 string like this, it corresponds to like xi type of string for a stabilizer. Okay, so it turns out this convention is very useful if we want to like derive the phase gate of the code. So I want to explain this transversal gates in a top-down manner. So here, I will show you first why these constraints on the X stabilizer weight will give you rise to the claimed logical gate. So note that the X logical representative for both codes can be written down as all 1. And let's only focus on this D=7 code. So a T gate acting on computational basis state gives a phase like this. And if we want to prove that a transversal T gate acts as a logical T dagger gate, we just need to prove something like this on the logical states. Okay. So the zero logical state can be obtained by initialize all the qubits in 0 and then apply all the stabilizers to it. And these stabilizers are doing nothing, so you are left with X stabilizers only. So the zero logical state is the uniform superposition of all the X-type string. And if you act the transversal T on each of this stabilizer string, it effectively gives you a phase which is proportional to the weight of this string. And since I assume that every X stabilizer has weight divisible by 8, this phase is trivial for every string. So the transversal T acting on the zero logical state is effectively 0. Similarly, for the one state where we just apply this X logical operator to the state, and then here we see like if the weight of each string is 127, which is the length of the code, minus the weight of the original string. And 127 is minus 1 modulo 8. So this gives us this phase on the one state. Okay, so now I want to talk about some of the intersections. So I said that I assume every X stabilizer has weights satisfying this property, but then I will only specify the generators of the X stabilizer. So you might be thinking, do I need to take all the 2 to the m linear combinations of these stabilizer generators and then test for each one, do they satisfy this weight property? Turns out you don't need to do that. You only need poly-M testing. So let me first write down the necessary conditions for like every X stabilizer weight has satisfied this property. So first of all, each row is an X stabilizer, so they need to satisfy this property itself. And then if you consider the double intersection, it needs to satisfy this. This is because if you combine Si and Sj, you take the XOR of these two vectors, you count the support, you will see that the double intersection support was counted twice. So this explains this, why this is 2 here and why this is 4 here. And similarly, if you consider Si XOR Sj XOR SL, and you will see that by drawing Venn diagram, the support of the triple intersection was counted 4 times. So that's why here the triple intersection needs to has weight divisible by 2. Okay, so these necessary conditions turns out to be sufficient as well, and I will show you why. So this is enabled by this very powerful identity. So let me explain it a bit. So on the left-hand side, this A1 to AM, there are binary variables. So they take values from 0 and 1, and then you are XORing them. So the left-hand side will be a value in 0 or 1. But on the right-hand side, you are taking multiplications of these binary variables. Multiplication means and also you are doing all the arithmetics over Z. So like times 4 minus plus 0 all over Z. So this turns out to be true. It actually can be checked by induction very easily. And I also want to comment that the coefficient here will always be a power of 2. So it will be like 8, 16, and so on for even more intersection. So now let me explain why this is sufficient. So let me do it like using 3 qubits only. So we write down the stabilizer generators like this. And then we can consider, like, for example, the linear combination of all of them. It's just like this. And then we count the weight. So this weight is, again, counted over Z2. And then for each XOR of AJ, we do it using this formula. So we're gonna apply this formula like vertically for each column. And we end up with something like this after some manipulation. So notice that the first term is just weight of Sj, which is quite obvious. And the second is weight of the double intersection, because if you take the intersection, it will be something like this, and this is the weight. And similar, this is the triple intersection. And now if you ask me what is the weight of this linear combination modulo 8, you will see that I never need to consider terms after this. So this is why triple intersection suffice for this test of modulo 8. Okay, so this formula is very powerful, and it actually allows you to derive something like this. So give me a CSS code specified by logical generators and stabilizers. I want to ask the question whether t to the gamma 1 up to t to the gamma n could be a valid logical gate of my code. So I will call such a gamma a metric. And this formula will allow you to find all the valid gamma. And for each valid gamma, it also allows you to derive the logical action of this t to the gamma gate. So if you are interested in this question, you can see about 2 pages of our phantom code paper. I want to comment that this is actually not something new from the literature. Like there's this XP formalism paper that actually already did this. But here we repackage it into the phase polynomial language, so things become more concise. Okay, so going back to our main goal, I want to show you that these two codes can do transversal S or T gates. And so the condition I wrote down is that they need to satisfy this. And now the next step is to give you a set of X stabilizer generators such that up to triple intersection, they satisfy this constraint. And the X stabilizer generators will turn out to be subcubes. So let me define subcubes. So consider a Boolean hypercube. So for example, this one is in 2 dimensions, this one is in 3 dimensions. So we can label the coordinate of this Boolean hypercube into a string of m bits if the hypercube lives in m dimension. And then this is a subcube. 0, star, star. So star means it can take some both 0 and 1 value. And this is also a subcube. And in general, a subcube that lives in an ambient m-dimensional space is a string, takes value on 0, 1, and a star. And the dimension of the subcube is just number of stars. So another example, more exotic. So this is in 7 dimensions, and it has 3 stars, so it's a subcube of dimension 3. Okay, so now we can consider indicator vector of subcube, which will be our code words. So as an example, so here I write down all the coordinates of my 3-dimensional hypercube, and I consider this subcube, star, star 1, and the indicator vector is just which point does it contain. So it will be something like this. So the last coordinate will have to be 1, but you have like freedom in the first 2 bits. Similarly, the full cube is just all 1 vector, and some other examples like this. Okay. So an important property of this indicator vector is that the weight of this indicator vector is just 2 to the number of stars in the string. Yeah. Okay. So now I want to make the connection of an indicator vector to evaluation of a function on hypercube. So let me give an example. So here I wrote down the function like this. And here I'm going to replace x3 equals 1, x2 equals 1, x1 equals 1 into this, and then evaluate this function at this point. So it will be 1 times 1 plus 1 times 1. And in F2, it's just 0. So for the next point, 1, 1, 0, we have 1 times 1 plus 1 times 0. So it's 1. So similarly, like this, you can get the evaluation vector of this polynomial. So for the subcubes above, you can do similar things, and you can see a connection between the evaluation of a monomial and a subcube. Basically, if, for example, here 1 is present at x1, then you just put x1 here. And here, both x2 and x1 are present, so you put x2 and x1 here. And so we can describe subcube by monomials. And because on the previous slide, I also allow like 0 in the subcube string, and you can do it by using this negated variable. So, but it's not very important for this moment. Let's ignore that. And so here, you can see that the plus here on the function is actually just XOR of these two indicator vectors. So this two XOR to this. And the reason why I switched to this polynomial formalism is that if you consider XOR of subcube, it may not be a subcube itself. So using polynomial formalism is much simpler in terms of this XOR. And this will turns out to be important in the phantom code construction. Okay, so now we already observed this connection between subcube and monomial. Again, it's by the presence of the variables. So we also have the links between their weight. So weight of the indicator vector is 2 to the number of stars. And for this, weight of the evaluation vector is just 2 to the number of missing variables. So for example, here I have 7 variables in total, but now I miss 4 of them, x3, x4, x5, x6. So the weight of this will be 2 to the 4, which is 16. And it aligns with this. Okay, so we've seen on the previous slides that XOR of subcube is equal to addition of polynomials. So just a few comments. We are doing things in the binary field now. So 2 times everything is 0, and plus makes no difference as minus. We will only use this polynomial later. Now we focus on monomials. So now we can talk about intersections. So intersection of subcube, you can see if I have both 1, I just take 1. And if I have 1 and star, I just take 1. If I have star, star, then it's star. So easy. And it turns out like the corresponding operation in this polynomial formalism is just multiplication. So this is an example. So for example, here we just multiply these 2 monomials. We get to this. And these are binary variables. So the square of itself equals itself. So we just remove all the square, and it ends up with this, which is, as you can check, the same as this. Okay. So later, okay, not for this talk, but if you are interested, if you are considering like intersection of XOR of subcube, which is really exotic, then it's very simple in this polynomial formalism. You just multiply those polynomials. Okay, so we will only use these rules for the transversal S or T gates. So let me reformulate a bit. And now we can get to this transversal gates. So first of all, for this D equals 15 code, I will give you a basis of X stabilizer that satisfies this. So it turns out that you only need evaluation vectors of monomials of degree in 1, 2, 3. So we don't need 0 because 0 is the degree 0 polynomial is just the constant 1. And this was taken as the X logical. And for this punctured code to happen, we will puncture this coordinate. By deleting it, this all 0 delete coordinate. So to be more explicit, here is just the evaluation of those monomials up to degree 3. And if we puncture coordinate 0, it doesn't affect them because they all evaluate to 0 at this coordinate. So now we can check whether they satisfy this 2 constraint. So if you take each of the SI, then you will see that each of them miss at least 4 variables because the degree is only up to 3. So the weight of it is 2 to the 4, at least divisible by 2 to the 4, which is 16. And so the first one is checked. And if you consider the second constraint, where we just need to take the intersection of the 2 monomials by multiplying them, you will see that if I multiply 2 degree 3 monomials, I will get a degree 6 monomial at most. So it will lack at least 1 variable. So the weight of this intersection is divisible by 2. So this is checked. So every stabilizer weight divisible by 4 is checked. And I just want to comment that for this code, we can take the Z stabilizer to be equal to X stabilizer because of the second constraint. So this, together with the fact that both X and Z logical are all 1, transversal H is valid logical in this code. Okay, now we get to this distance 7 code. So here, again, like X logical is evaluation of 1, and we need to check this. And the basis of this is evaluation vectors of monomial of degree 1 or 2. So like this. So similarly, we can check the constraint. So first one, missing at least 5 variable, and second one, so multiplying them give you degree at most 4, so you lack at least 3 variables. So this double intersection will be divisible by 8, actually. And then finally, you just need to check the multiplication of the 3 monomials. And since each of them is degree at most 2, you have the product is of degree at most 6. So you will lack at least 1 variable. And this will give you this weight divisible by 2 here. Okay. So these are the code words, X stabilizer and X logicals of these codes. So the Z stabilizers, if you derive a basis of it, you can see it's something like this. So again, degree 4 times degree 2 is degree 6, so you will lack 1 variable, and so they commute. Okay, so what I've just said is this evaluation picture is basically this Reed-Muller code in dimension m and up to degree Rx. So it contains the evaluation vector of all the monomials of degree up to Rx. So the distance here, I'm not going to prove it because it's not really relevant for us. So to construct the quantum code, we just take the first row as the X logical and the rest as stabilizer generator. And then we puncture the all 0 coordinate. And then we leave this out, and this quadrant here will be the shortened Reed-Muller code. From the definition, it should not be hard to see that it satisfies this containment relationship because it's degree up to R and R prime. And let me just be more explicit about this thing. So this is actually the X logical and X stabilizer of the sting code. It can be explained and obtained as follows. So I will puncture this, and I only focus on this. So this is the sting code, the 713 code. And so yeah, the first one is the X logical. So this gives you a way to define this punctured quantum Reed-Muller code by imposing that the X and Z logical operator to be all 1, and the X stabilizer to be this shortened RM code, and Z stabilizer satisfied this so that they commute, because you will always lack 1 variable when multiplying them. So the parameter of this code will be as follows. So 2 to the n minus 1 physical qubit, and only one logical qubit can be obtained like, if you do some dimensional counting. And the distance of the code is like this. Okay, so as some well-known example, the Sting code, as I've just said, is Rx equals 1, Rz equals 1. And the 1513 code for magic state distillation, for example, is just Rx equals 1, Rz equals 2. And this, the pair distance 15 and 7 pairs has parameter like this. And a trick to remember like what logical gates they can do is as follows. So if you have Rx equals Rz, basically your X stabilizer and Z stabilizer are the same, then this code emits transversal Hadamard. And if 3Rx plus 1 is less than or equal to M, then this code emits transversal T. More generally, you can also prove that if nu times Rx plus 1 less than or equal to M, then this code emits transversal Z rotation like this. So higher level Clifford hierarchy. Okay. So now we can go to this transversal code switching, which was actually proposed in this 2013 paper. And they formulate it as a way of doing logical Hadamard gates in this 1513 code. So we all know that this code can do transversal T, and it cannot do transversal Hadamard. So how does it work? So the author suggests that you just do transversal Hadamard like this, and then you prepare another block in the plus state, plus logical state, and then you do transversal CNOT between them, and then you do Sting error correction. So why is this transversal code switching? So let me redraw the diagram. It should be a bit simpler. So this is the idea. And as I've said before, this is this punctured QRM codes, and let's put them there. So after this Hadamard gate, the X sector and the Z sectors are swapped. So you end up with this code actually, like 214. And the logical states is actually Hadamard times this psi. So now basically you are just doing code switching from this code into the original code. So let's just rewrite the state as phi. So how does it work? So this follows because of this containment relationship of the stabilizers I stated before. So basically, if you look at the X and Z stabilizer, they satisfy this containment relationship. And then you can see that this code lacks some Z stabilizers. And you can get them by copying them from this bottom plus code. So basically, this is copying these are Z stabilizers. And the X stabilizers, you have some extra X stabilizer here, and they are going to propagate to this transversal measurement and being caught. And these extra X stabilizers are treated as noise. So it's basically corrected using Sting error correction. So through this argument, you can derive that you are ending up in the original code state. So basically, the same thing worked for this 127 pair by exactly the same reason. So now I actually only want to focus on this direction of code switching, because if you substitute this phi here by the T state, then you can get the T state on this self-do code, which can do transversal Clifford, and then you can later just teleport this T gate into the symmetric code. So only this direction is enough for universal computation. So let me just focus on this. And I want to give you an alternative interpretation of this using teleportation. So the idea is to view these two codes as two different gauge fixing of a common parent code. So this common parent code encodes many logical qubits. But because of this X and Z stabilizer containment relationship, you can view as like some of the extra logicals are set to the 0 logical state. And here you have some, for example, some extra X stabilizer, so things like this. And then because the parent code are the same and it is a CSS code, you can do transversal CNOT gate. So this is just the usual transversal CNOT gate. And then you can see that these two CNOT are effectively doing nothing because they are controlled by 0 state. And then this, on the first Y of the 2 blocks, it's actually just a teleportation gadget. So you will basically teleport this plus state to the top. And you end up in the correct gauge you want. Okay, so actually this teleportation picture allows you to see that CNOT can go both ways. So this is a bit different from if you know 2D to 3D color code switching, where the CNOT is only one way. So in this code switching picture, CNOT can go both ways. So let me explain why. So again, we consider this parent code and we write down something like this. And then you see these two CNOT are doing nothing because this is a target on plus, this one is controlled by 0. And this is actually another teleportation gadget, by teleporting this phi to here. So you again end up in the correct state. Okay, so this is basically transversal code switching. One thing you can do, you can easily see from this picture, this teleportation picture, is that if you want to generalize this transversal code switching idea to k bigger than 1 code, then it's also very simple. You just like make more lines here. And this is basically just teleportation of this phi state, which is on more logical qubits now. Yeah. Okay. So this finished the first part. Let me check time. Okay. Now we get to phantom codes, which encodes more than 1 logical qubit. And the definition of it is that we can do any logical CNOT circuit by permutation only. And the motivation of studying them for me personally is that I want to know that like what can we gain from imposing this very stringent constraint on the logical gate, and what are the limitations, like certain no-go theorem will be the best. Okay, so one example phantom code is the well-known 422 code. It has a stabilizer logical as this. And if you consider the permutation of swapping qubit 2 and 3, then first you will check that the stabilizers remain the same. So the code space is preserved. And then to determine the logical action, you just basically, like for example, x1 here is this, and then you swap x2 with x3, you see that logical x1 is mapped to logical x2, and vice versa. So the logical action of this is effectively swapping the 2 logical qubits. Another example is this cyclic permutation. This will end up to be a trivial logical action, as you can check. So not all the permutations are relevant for us. So as I've mentioned before, this phantom QRM code was obtained from this high-rate family, which is defined as follow. So I will take the hypercube in dimension 2R. So the code length will be this. And then for the X logical generators, I define them as degree equals R monomials. And the X stabilizer generators are degree less and equal than R minus 1 monomials. So one thing you can check is that X stabilizer generator is this, because again, if you multiply these 2 monomials here, you will lack two variables, and the weight of the intersection is divisible by 4, so they commute. So a few explicit code parameter, if you do dimension counting, it will be like this. So the rate is really very high. And so, as mentioned before, later I will gauge out a few logical generators, and in order to understand what I really mean, we need to digress into the unitary encoding picture of QRM code. So this is an hypercube encoding circuit. So basically, you just take this CNOT and repeat it in certain pattern. And here, I write down the coordinates of this hypercube in 4 dimensions. And then here, correspondingly, I also write down all the possible monomials. So you can see one correspondence is, again, this presence of variable versus this ones here. So again, this is to be read in x4, x3, x2, x1. So how does this relate to the encoding? So if you put 1 here on a certain row and view this as a classical CNOT circuit, and you propagate this 1 through, you will see that the ones at the output side form the subcube labeled by what's on the left. So you can check this using induction. So for now, just believe me on this. And then now we can go to this quantum code picture, where again we just do stabilizer propagation. So if we put a plus state here, which is stabilized by a single x operator here, and you propagate the stabilizer through the unitary encoding circuit, you get a stabilizer of the code. And similarly, if you do, if you want to get the z stabilizer, you can also propagate it through. And the propagation rule here is that at the output side, you will get, again, a monomial, but the negated complement of what is labeled here. So complement means that I just take the full polynomial, like x4, x3, x2, x1, and I divide it by this. I get x2, x1, and then I take negation of each variable. So this stabilizer propagation picture also allows one to derive XZ logical pairs. So let me just specify how to unitary encode for certain QRM code. So for example, for the 1664 code, where the X logical generator are degree 2 monomials, and X stabilizer generator are degree less than 1 monomials. For X stabilizer generator, you just circle out them, those monomials, and then you put plus here. And you are guaranteed to get the corresponding stabilizer at the end. And for the logical generators, you just allow arbitrary quantum info here. And for the rest, you just assign them as 0 states, which will give you the stabilizer generator at the end. So this is the unitary encoding circuit of the entire quantum Reed-Muller code family. OK, now we can get to code automorphism. So first of all, on the classical Reed-Muller code side, this is an automorphism of the code. So here, you interpret it in 2 ways. First of all, it is a permutation of the coordinates. So to give an example, if you take A to be something like this and ignore B, and you substitute 111 here, 111, and you multiply them, you get this to be 100. So this AX plus B thing here is a coordinate permutation. And you can also interpret it as a polynomial transformation. So the idea is to substitute each X variable by its prime. So as an example, again using this, so if you have x3, x1, and x3 is mapped to this times this, so it's x3 plus x2 plus x1. And x1 is mapped to this times this, so it's x2, sorry, there's a typo, x2 plus x1 here. So this is how you get the transformed polynomial. So why is this an automorphism of the classical RM code, where again, RM code of order R is degree less and equal than R polynomials? This is because this AX plus B transformation here does not increase the polynomial's degree. So something you can check via this very easily. So this preserves all the code word. And it is also invertible because I require A here to be invertible. So it's actually an automorphism permutation. So now what if we apply these automorphism permutation to the quantum Reed-Muller codes? So this coordinate transformation, basically we just permute qubit, and the polynomial transformation tells us how to map the stabilizers and the logicals. So as an example of this QRM family, we can consider what is known in the literature as the hypercube code. This is actually a phantom code. So the X logical generator can be written as those monomials, and X stabilizer generator is just 1. And if we consider this AX plus B, again, ignore B, and you can see that, for example, this matrix is mapping XM to XM plus XM minus 1 while leaving others unchanged. And if you plot out what's the logical action of it, so here I'm plotting those wires of those, this M logical qubits, and you will see if we are to derive this final transformed polynomial, this corresponds to a CNOT action like this. So perhaps you already noticed that this A matrix here for the transformation, 1-to-1 corresponds to any logical CNOT circuit, a given logical CNOT circuit. So this is basically what gives you the phantom code property. So another example is to obtain this 1634 phantom code from this parent QRM code, where for the X logical generator, you have this 6 degree 2 monomials, and stabilizer generator are degree 1 or 0 monomials. So again, concrete example, so here A is like this, and then the mapping is like this, others are invariant. And if you plot out the 6 logical qubits, and then you calculate what's the transformed polynomial, you will see something like this. So for example, here is just replace this x4 by x4 plus x3, so transformed polynomial is like this. And here, this x3, x4 remains the same because this x3, actually x3 squared, which is equal to x3 because it's binary variable, is equal to itself because x3 is a stabilizer of the code. And similarly, you can derive the follows. So if you plot out this logical action of this, it is a pair of CNOT gates. So it is not as expected as I want, only a single CNOT gate here. So more generally, if you choose the automorphism permutation to be, you have this top left quadrant to be invertible 3x3 matrix, and you leave this x1 variable fixed, you can get arbitrary CNOT circuit on the first 3 wires. However, the last 3 wires will also get some Hartman conjugated CNOT actually. And so this basically partitions the logical into 2 orbits. So by orbits, I mean these things transform under this automorphism permutation within itself, but not across the 2 orbits. So a way to get rid of this actual logical action is by fixing them to say all 0 or all plus. So because so if this is all 0, then any CNOT gate on all 0 input is just nothing. So yeah. So this A prime here on the top left quadrant corresponds 1-to-1 to this logical circuit on these 3 logicals I choose. So what do I mean if I say, I set these X logical generators to the 0 state? Basically, I mean, here, instead of allowing arbitrary input, I set them to 0. So I'm actually promoting the negated complement to these stabilizers. So this is what I mean by moving a set of monomials to 0 or plus state. So another example, so this one we actually perform a lot of numerics on this code, 6448. It can be obtained from this code. So this one, X logical generators are the degree 3 monomials and X stabilizer degree less than equal than 2. So here, we can, again, only consider a subset of automorphism permutation. Here, I will leave x2 and x1 intact, because see here, like every monomial I choose has this x1, x2 here. And this invertible top left quadrant acting on this x6 to x3 will correspond one-to-one to a logical circuit on the 4 chosen logical qubits. And so if we call this matrix A, then you will see, like, through some calculation, it divides all the 20 degree 3 monomials into 4 orbits. So for each orbit, you can promote them either all to 0 or all to plus. So you have the control of, like, number of X stabilizer and Z stabilizer if you want. So you can generalize this construction here and get a quite balanced code. By balance, I mean the number of X stabilizer generator and Z stabilizer generator does not differ by much. However, there's this obstruction that, like, you cannot reach exact balance. Because actually, I will mention this later, there seems to be a fundamental trade-off between K bigger than 1 phantom property and ZX duality. So you just cannot get exact balance from this. And so maybe from this code example, you can see that I can balance the code by promoting this into all X and this to all plus. But this, either if it's all 0 or all plus, I will basically the number of X stabilizer and Z stabilizer will differ. So this is the obstruction. Okay, so now, so this phantom code can do any in-block CNOT from permutation, and then we are gradually getting to the full Clifford group. So the first thing we want to do is an interblock selective CNOT. So this is enabled by this circuit identity. So this is across 2 blocks, and those permutations inside the block can be achieved through permutations. Okay, so actually, what you can prove is that any interblock CNOT circuit, not just this very simple one, and no matter how complicated, as long as all the CNOTs are aligned in the same direction, it takes depths at most 2. So this depth is this transversal CNOT here. So if it's a permutation, then we ignore the depths because it can be compiled as relabeling. And what you can also show that any CNOT circuit, again, like no matter how complicated it is, on B blocks of phantom code, of the same phantom code, takes steps only this to implement. And you can see that the steps is independent of how many logical qubits your phantom code is encoding. So this is why it can speed up permutation compared to, for example, you have B times K qubits encoded using B times K blocks of surface code, then there exists some CNOT circuit, very complicated one that can take you the steps to implement. And this is by counting argument. And this is by a constructive proof. So you can see that basically this phantom code is saving you by a factor of K in terms of the depth. And this is as desired, I would say, because it can do arbitrary in-block CNOT from permutation. Okay, so this is one example of speeding up the computation. And I just want to quickly remark that if you consider this trick of interleaving permutation with CNOT, transversal CNOT, you can get a larger set of logical CNOT circuit than what you can normally do with only in-block permutation. So I will skip this. For example, even on this very high rate code family, which are not phantom, you can achieve arbitrary CNOT circuit through this trick, which is introduced in this paper. But the caveat here is this, the depths of doing those circuits are really, really high. So that's why we do this phantom code project. And so next, a bit more things with this selective CNOT, what you can do. So for example, you can do this mixed basis state preparation. So here, this is actually, again, a teleportation circuit on the first pair of logical from 2 blocks. And you can also do a selective S-gate teleportation. So for example, if in your code you can do SS via some folding, then you can get single logical S via this selective CNOT gate. Okay. I'm not going to show you how the full diagonal gates look like, but the claim for our phantom QRM codes is that you can actually do fold SISJ and arbitrary fold CZ using this depth 1 folding circuit, but they are not distance preserving. So I just want to mention that, like previously, you usually requires a code to have certain ZX duality for you to fold a gate, but it's actually not really required. Yeah. And so to get to the full Clifford group, we are still lacking Hadamard. And this is a gadget to get it. So let me explain how to do it. So this is on the left-hand side, this ancilla block, it can be achieved through this mixed basis preparation using selective CNOT. And then this gadget here is actually a CZ gate. So if I replace it by that, then on this first pair of logical, it is effectively this Hadamard teleportation gadget. And on the rest 3, it is this usual teleportation gadget. So you see that here, all the logical measurements are performed in the X basis. So this can actually be performed as a transversal X measurement. And then you decode and then do the feedback. So this is how you can get an addressable Hadamard, actually in O1 depths, but the depth is, O1 is not 1, yeah. So quick remark that if you want to do CCZ in this phantom code family, you can do it by decoupling down to a hypercube code, and then do CCZ there using like T or T dagger on a subcube, and then couple back. But the limitation is that you only have, you can only guarantee like distance equals 2. So there are many limitations of phantom codes. So first of all, we suspect that K must be logging N. And because my wonderful collaborator Jiming, he enumerated all the CSS code up to length 14, we actually confirmed this is true for K smaller equal than 4. And also, I showed you a scheme of like O1 depth for doing single S or Hadamard, but O1 is not 1, so the depth is actually very high. And also, I would say like the biggest obstruction for us, like headache for us, is the fold diagonal gates are not distance preserving. And you can see that it drops the X and Z distance differently, and also differently for different fold gates. So like a way maybe to overcome this by paying more overhead is to do a distillation circuit. So this is a 622 code, and it can do transversal S gate. So you can encode into this code and then do fold S and then unencode and then do the distillation. And then coming to this kind of no-go theorem, we can prove that this transversal Hadamard, physical transversal Hadamard, cannot give you any logical Hadamard gates up to any logical CNOT. So there seems to be a real obstruction for doing transversal Hadamard for this K bigger than 2 phantom codes. However, I want to remark that there are like certain subtleties here. So for example, what if you do not address every physical qubit here, you only address a subset of them. And here, this logical CNOT will be a permutation. And what if you are allowing like permutation that is not a valid logical? And those kind of subtleties need to be clear in the future. for this no-go. And then so there are two codes I want to highlight from our paper. So these two codes can actually do addressable S gates via applying S on a subset of qubit. However, you see that the parameters of those codes are not so attractive. For example, this one, you might as well use like 2 patches of Sting code. So, but in the future, we still want to generalize this family of codes, which is very interesting, and especially the CS magic here. Okay, and let me check the time. Okay, let me skip this. So I just want to quickly comment on the implementation. So all the codes I showed you before are not LPC codes. So we need to do Sting error correction for them. And so the basic building block is the unitary encoding circuit or state preparation circuit. For example, you can also do state preparation for this punctured QRM code by just removing this bottom Y and all the associated gates. And yeah, so I just want to emphasize that this is a plus and 0 and plus preparation circuit for these punctured codes. So it's not an arbitrary state unitary encoding circuit. However, for this high rate code, it is an arbitrary state unitary encoding circuit. And then for fault-tolerant preparation, we can do this flagging. Where's my flag? Yeah. So the problem with this encoding is that the single error could propagate to a high weight one. So you will consider doing some flagging using 2 patches. However, if you just do nothing and use 2 identical encoding circuit, if the fault happens at the same location on the 2 code block, they will cancel exactly. So this gives you an example of 2 faults happen, but a wait 4 error remains. Think of it in a higher distance code, but not the Sting code. And so a way to overcome this was proposed in this paper for Galilei code, where they said that what if I permute at this site by certain automorphism that preserve the code, then I can still do this flagging. And this permutation here, effectively, if you consider the action of the residual error, previously they are the same if you don't do any permutation. And the permutation are just move them apart so that you don't get exact cancellation here. So it will give you a higher suppression than p squared. So basically, I just do the same for both this k equals 1 code and the phantom codes by using this 4 to 1 flagging gadget. And on this, after this encoding circuit, we apply 4 different automorphism permutation. And some nice pictures. So this is for the k equals 1 codes where I optimize it using this atom movement. But for the phantom code, it's basically the same preparations. And last thing I want to show you, this is really cool. This is really the highlight of the paper, actually. So we are told that Sting EC is single shot. This means that if you just look at a single round and you do the correction here, you can get this desired suppression. However, the constant in front of this will be pretty bad because everything here is noisy. So for example, if you consider this measurement noise only, and then if you have this residual error on this input side, this measurement here will see something like this. And then because the decoder doesn't know which error comes from the measurement error, it will undo all of them. So it will undo this measurement error as well. So it will inject this into this state. So this is pretty bad. So we asked the question can we only undo this E error here, removing this measurement error? This is possible if you look across 2 rounds. So for example, if I temporarily, I don't correct at this end, and I allow this residual error to propagate through. And we have, again, some measurement error here. And then here we can look at them. and decode them together by treating this actual residue error as the correlation. So this actually gives us a 50 times reduction in logical error rate in our numeric benchmarking. And you can similarly do things if it's across gates. So for example, here you can decode it like this, and then commit to this error, propagate it through, and then like decode this using correlated decoding. And then this is actually another interesting fact we discovered. Like we also consider MLE across this whole window. So the MLE can look at the whole 8 rounds of stinging error correction. But then we find out it only gives us a 2 times performance boost compared to decoding across 2 rounds. Okay, so okay, I can conclude here. Yeah. Yeah. Thank you for listening.
Thanks very much. Do we have any questions? We have time for some quick questions. I had a question while people think. So you said that for these codes where you permute to get CNOTs, that there's probably a limitation that the number of logical qubits is like log the number of physical qubits. I was wondering if you had any intuition or thoughts about the limitations on distance. Mm-hmm. So can the distance grow as I grow the number of qubits, and how fast?
So distance is not really limited. So one thing you can do is you take an arbitrary phantom code and you concatenate it with a k=1 code, for example, surface code. Then the code is again phantom. So for this concatenation, you can use a very high distance k=1 code. So distance is not limited. Yeah.
Thank you for the talk. I like this idea about the single shift stinging error correction. It reminds me a lot about like how you do like single shift decoding in like memory-based computing, where you also have to like syndrome errors from 2 rounds, and you basically just look at the errors that happen in between rounds. Is it like analogous, or is there like something where it's like analogy breakdown?
Okay, so I think the measurement-based thing you're talking about, like, if you're only using Bayer and Silla for decoding, then if you don't decode across round, then you cannot see this P to the T suppression. Yeah, it's kind of fundamentally limited there if you only do single round. Because like, yeah, this flip on the measurement might actually not be an error. So you might decode completely wrong if you only look at one round. But sting error correction is like, you can guarantee this suppression even looking at one round.
Okay, I think we should thank the speaker again.